Hello everyone, let's talk about ellipses. Now the ellipses are the familiar oval shape that I'm sure everybody is familiar with. The literal meaning in Greek of ellipse is deficiency. I don't think it has anything to do with the ellipse, and that is not deficient in any sense that I'm aware of. The formal definition of ellipse you're looking at, and by the way, here's how the ellipse could be created, right? Is when the flat plane or surface crosses one nap, only one nap, the upper or lower nap of a double napped cone at an angle, so that again the impression that it leaves outside of the cone is going to be an elliptical or oval shaped. The formal definition of ellipse follows, in that an ellipse is the locus of all points in a plane, the sum of whose distances from two fixed points called the foci is constant. Now the word here in bold, by the way, that's not foci, it's foci. It's literally the C is pronounced as an S here. So we have foci, which is the plural form of focus. Focus, foci. All right. Sum of whose distances from two fixed points. So this would be the distance on this drawing. These are the two distances. Call this D1, D2. D1 plus D2 equal to a constant, and that would give you the ellipse. So any point that qualifies for this. So for example, if I look at the point here, because it's on the ellipse, if I add the distance from one focal point, the distance from another one, again, call it D1, D2, that total will be the same. Let's take a look at the point here. This would be, say, D1, and this is D2. The sum of those two will be fixed. So as long as we can find points like that on a plane, then those will qualify as points on the ellipse. Okay, now see here, looking at what the diagram that I have here. C here is the distance. This is important for identifying the equation of the ellipse. C is the distance from the center of the ellipse to a focal point, to a focus. Okay, so keep that in mind. In other words, the center of the ellipse here is at 0, 0. The distance from there to a focal point, that's C, and this would be negative C. And of course, C is positive here, right? We're taking C to be positive here. All right. Now, the general equation in the book, by the way, and online you can find, it's rather not lengthy, but in the interest of time, I'm going to leave that up to you to explore for yourself the proof for the equation, how the equation of the ellipse is derived. And I'm simply just going to work with the ellipses. Now, every ellipse has a major and a minor axis. Okay, the major axis is the longer of the two axes. So maybe I should use a different color. There you go. So that would be the major axis of the ellipse. And the minor axis of the ellipse is going to be this one. It's the one it's the chord of the ellipse that runs through the center perpendicular to the major. And we're going to call that the minor axis. Okay. Now, the end point of the major axis is where the vertices are, call them VV prime. And the end point of the minor axis, call it WW prime, is where the co-vertices are. So we have vertices and co-vertices. Now the distance from the center to a vertex, this distance is going to be A. The distance from the center to a covertex, that's what B is. All right. Now for an ellipse whose center is at 0, 0, the equation of the ellipse is x squared over a squared plus y squared over b squared is equal to 1. Now the 1 here is absolute necessity. We have to have a 1 on this side. It's very important to have 1. For everything we do relies on the fact that there is a 1 on that side. If it's not 1, we have to do whatever it takes to create that 1 on that side. Okay, and there you have the specifics of this. Now the relationship between A, B, and C for the ellipse is the following. This is an important relationship. So that C squared is A squared minus B squared. And because subtraction is not commutative, makes a difference which is A and which is B, because if the expression is less than 0, then we get imaginary solution, right? So we gotta be careful how to label A and B. Typically in the denominators, the one I have right now, what you see on the screen, A is greater than B. Okay, and A is greater than B. That guarantees that C would be positive. But there are actually different equations, 2 different equations for the ellipse. But I'm going to just give you this one, and then I'll tell you more about identifying the equations without giving you another additional equation. So let's just focus on this one for now. The longer of the 2 axes major, the smaller of the 2 minor axes. A is greater than B, and because A is in the denominator that goes with X, and I think of X as a horizontal direction, so here's a case where my ellipse is going to be horizontal ellipse. Again, by horizontal ellipse, I mean that the major axis is horizontal. So I'm going to label this my ellipse here now. This point is going to be A, not be A0, because again, center is at 0, 0, so it's going to be A0. This point, one of the co-vertices is 0B. Okay, and this is where C is. And that's the ellipse that goes with the equation that I have. Remember, vertices are the endpoints of major, co-vertices the endpoint of the minor axis. If A is greater than B, the way I have it here, then the major axis is going to be either parallel to the x-axis or the x-axis itself, depending on where the center is. For ellipses centered at 0, 0, the major axis is going to be the x-axis. Now, what if A is less than B? Then I'll show you how to handle those. Pretty much everything and the way I work these problems, as you will see, is by trying to plot the points given the information that I have, and do it that way. Okay, so let's do this then. Let's take a look at an example here. Okay, and in my first example, this is my first example. Let's say I want to find the important characteristics of the ellipse. Find the center. We want to find the vertices. Now, by the way, I mentioned about co-vertices, but in your book that I'm using, they don't mention co-vertices, so I'm going to leave that one alone. The coordinates of the foci, find center, vertices, foci, and graph. We're going to graph the following equation. Let's say my equation is x squared over 9 plus y squared over 25 is equal to 1. Okay. Now this one has center at 0, 0 because the way it looks. And by the way, the more general form, maybe I'll give that to you. I'll give it to you in just a moment, where the center is not at 0, 0. So for this one, center is at 0, 0. And in this case, by the way, notice 25 is bigger than 9, right? So whichever denominator is greater, This is important, folks. Whichever denominator is greater, that's going to be your a squared. There. If 25 was in the denominator of x squared, I would call that a squared. This way, you only need really one equation rather than two separate equations. And the other thing that's important, the 25, we see that as a number in a square form, namely 5. So from this, I know a is 5, and I know that b is 3. So do not square 25 again to get a squared. These are already in their squared form. Okay, now I can actually graph these easily, couldn't I? Let me copy my ellipse from above here down below, and I'll do it for you. Okay, so here you go. I did a copy paste job here. Now the center again is at 0, 0. Let's write the specifics here. I know I wrote it earlier up here, but let me move it to the left. So center is at 0, 0. Next, we want to find the vertices, right? The vertices, those would be the endpoint of the major axis. So in this case, a is 5. So that's going to be 5, 0. The other one is at negative 5, 0. So my vertices are at, now I would write it myself as plus minus 5 comma 0. So I only have to write it once. Or you can write it as two distinct points, negative 5, 0 and 5, 0. Okay, so I have that. What about the foci? Well, to find the foci, the coordinates of these focal points, foci, we need the relationship c squared is a squared minus b squared. And remember, a squared is the larger of the two denominators. B squared is 9, and that's 16. Therefore, c would be plus minus 4. And that's what this is. Here's 4, here's negative 4. Cool. And so the foci, once we have c, we have the foci. The foci has coordinates plus minus 4. That's c and 0. Again, you can split it like the one above into two distinct ordered pairs. And what else? That's it. We have all the key information that we wanted to do. Center. We have the vertices, and we have the foci. And here's the graph, of course. Perfect. Let's take a look at another example. Okay, so for this next example, this time, let's say we want to find an equation of the ellipse. Let's say the ellipse has center at 0, 0. Focus is at 0, negative 4, and the vertex is at 0, 5. And simple. Find an equation of the ellipse. All right. Now, let me again plot these points, and the graph really helps me, folks, and I highly encourage you to do it from the graph. Once I plot these points, then we can identify the A, B, C's much easier than looking at just these numbers. So let me do that. Great. Let's start with plotting points. Again, center is at 0, 0. That's the center of the ellipse. And focus is at 0, negative 4. 1, 2, 3, negative 4 is here. 0, negative 4. And the vertex is at 0, 5. 1, 2, 3, 4, 5. Vertex is up here. This is 5, and this is negative 4. Now remember, there are two foci. So if one focus is at 0, negative 4, the other one would be up here, wouldn't it? At 4. That would be the other focal point right there. And what is that we just found? Well, we know C, and please do not confuse this C. The C I have here means center. The C that I have here, this is the distance from center to focus. That's what that is. Okay, so we know that C is 4, right? For the one that's along the y-axis. And the fact that the vertex is 0, 5 means the other vertex is at -5, isn't it? 0, -5, so we have the two vertices. And finally, if you look at these points, these are collinear, and vertices are the endpoints of the major axis. So I know that this ellipse is going to be a vertical ellipse, right? Major axis is vertical. Okay, because I'm given vertices, and those happen at the endpoints of the major, not minor, major axis. So now I can throw in and I can actually graph my ellipse. The only thing I need now is I have the A, right? A is 5, C is 4. What is B? Well, the equation is C squared is A squared minus B squared. And remember, A is bigger than B here. C squared is 16. A squared is 25 minus B squared. Subtract 25 from both sides. Divide by -1, and we get B squared is 9. So the center is at 0, 0, and the equation is going to be x squared over the smaller of B squared is 9, A squared is 25, right? Because this is a vertical ellipse, so A squared will be the denominator on y. There you go. So 9 has to go with x equal 1. And there we have the equation of the ellipse. And we can actually graph the ellipse. And let me grab my oval shape and do a good job of the ellipse for you. And here you go. I just again created this oval shape. There's -4. And here's the graph of the ellipse. This distance again from 0 to 3, that's B, that's -3, up here 5, and down here -5. Right? Not too bad. Fairly easy. And we are done with this example. Let's take a look at another one. Now for this next one, I'm going to still keep this at 0, 0. Then I'll give you the general equation for the ellipses that are not centered at 0, 0. I'm going to give you the HK form of those. So let's take a look at one more example. In this example, suppose now I want to find the equation of the ellipse. Suppose the foci are ±2 and 0, and the major axis in this case has a length, major axis length, I'm gonna make it 6 equals 6 units. Okay, and that's it. And let's go center at 0, 0. All right. Or how do we know? Let's see if we can do it without center at 0, 0. Well, the foci are at ±2, 0. So let me graph based on what I know so far. So +2 -2. That's 2 - 2. Well, these are the foci. So indeed, the halfway between is the center, right? So from this, I know center is at 0, 0. The major axis length is 6. So that means the distance from there to there, the endpoints of that, remember, are the vertices, VV prime. And we know this length is 6 units long. From here to here, that's 6 units long. And I think we know enough to do this work. Well, that means what is A? A is the distance from the center to a vertex. So A is 3. Correct? Based on major axis length 6, half that is going to be A. And then we know C. C is 2. And the equation we had is C squared is A squared minus B squared. And because this is going to be a horizontal ellipse, right? That's the upper part, and let's say this is the lower part. It's going to be a horizontal ellipse. So I'm going to write c squared. That's going to be 4 is equal to a is going to be the larger than b here. So a squared is going to be 9 minus b squared. Subtract 9 from both sides, and b squared must be 5. So the equation of this thing is going to be x squared over the smaller number goes with y, right? Again, because the major axis is horizontal. X squared over a squared, so x squared over 9 is equal, plus y squared over b squared is 5. Again, don't square that in the denominator of the equation. Equals that all important 1. It's always 1 on the right side. Okay. And up here, this point, if you will, that's square root of 5. This one is negative root 5. And we have these key points. So the vertices are at y is 0. So it's going to be plus minus 3 and 0. Perfect. And we got the equation of this thing. All right, so fairly easy. Now let's take a look at ellipses that are not centered at 0, 0. In general, if the center of the ellipse is at hk, then x minus h squared over a squared plus y minus k squared over b squared equal 1, which we can get by transformation of the ellipse, right? Right shift h shifts it to the right, and k shifts it in a vertical direction up or down, depending on if k is positive or negative. But nonetheless, there you go. That's the equation. All right. And let's take a look at an example of this kind of ellipse. And suppose now I'm going to do one where I don't have the standard form, the HK form. Suppose I'm given the polynomial form, and let's go with this one. Okay, and for this, we want to find the center, the coordinates of the foci, and the vertices. So how are we going to do this? Well, I need to get the HK form. That means I need to group my x and y's together. The number, we're going to ship it to the other side. So once I group them together, and remember, we're about to complete the square, right? So in anticipation of that, I'm going to factor 4 from y squared and 4 from 8. And the reason for that is because when we complete the square, the coefficient in front of these squares must be 1. And what do we add? 1/2 of the coefficient. In the case of x, coefficient is 4. And then you square it, so that will be 4 again. That's what we add on the left side. And so I don't forget it, I'm going to add 4 on the right side also. In fact, let me use a red color. So that's why we need 4 on both sides. And then what about with y? Well, 1/2 of negative 2, that's squared. 1/2 of negative 2 is negative 1, squared is 1. So I'm going to add plus 1 and add 1 on this side. All right, and there we go. So on the right side, we're just going to have 0 to the right. What do we have on the left? With the x, I have a perfect square trinomial on the left, so that'll mean I can write it as a square of a binomial, x plus 2 squared plus 4 times, within parentheses, I have y minus 1 squared equals 0 on the right side. Those are the binomial form of that those quadratic forms. Now, sorry, I didn't mean to have 0. I gotta have 1. Okay, now I don't need the 4 here, right? So, and let me make sure I did this. Oh boy, big mistake. I fell into that trap myself. See, because I added 1 inside parentheses, I put 1. I did it too quickly. there's actually a 4 on the outside, right? Outside parentheses, which will distribute itself to 1. So when it distributes itself to 1, actually to the other side, I need to add 4, not 1. Again, because of that forced distribution of 4 on the outside to 1. So to the right side, I actually have 4, not 1. Now, remember the equation must have a 1 on the right side. So next step, I'm going to divide everything by 4. Everything on both sides, let's divide it by 4. And when we do, we're going to get the true HK form. That's x plus 2 squared divided by 4. These 4's cross out, plus y minus 1 squared. I'm going to write it over 1 because that's going to help me graph my ellipse, equal 1 on the right side. So that is the equation. Remember, the larger of the two denominators is a squared. So in this case, a squared is 4b squared 1. From that, I know c squared is a squared minus b squared. Therefore, c squared is 4 minus 1. Again, do not square the denominators twice. Therefore, c squared is 3. That means c is plus minus root 3. And what is c? C is distance from center to a focal point. Okay, now we can identify the center. The center of this ellipse is going to be at h is negative 2 and k is 1. Right? The reason it's negative 2, by the way, not 2, because remember the form is x minus h. So that's x plus 2. H is negative 2. See that? H is negative 2. It's opposite of what it seems within parentheses. So we got the center. That answers portion of our question. And we will graph it in the end. The foci, well, how do we find the focal points? Well, the foci, I'm going to put C because it's pronounced with an S. So I'm going to put C there. The foci is going to have what? Again, that's the distance from center to, that would be center to C, right? So the foci will have coordinates. The center is at negative 2, 1. Let me do a quick graph here. Center is at negative 2. I'll fix this graph in a moment. I just want something workable. So see, this is the center. And because the greater denominator is 4, so this is going to be a horizontal ellipse, right? The major axis will be horizontal. The distance from center to a focal point, let's say this is root 3. Okay, this is going to be root 3. To this point, a focal point, the other focal point here. Therefore, the foci all going to have the same, have y, right? These are all collinear points. They have the same y. The foci is going to be at negative 2 from the center. Go to the right and to the left, square root of 3, and the y is 1. That'll give me the foci. Again, I'll do a good graph of this for you in just a moment. The vertices, well, the distance from the vertices, that's going to be from the center, right? From the center, which is at negative 2, 1. And A is 4. So it's going to be negative 2 plus or minus, oh, A squared is 4. A is 2 plus minus 2. Right? Those are the vertices, and they have the same height, 1, because those are collinear points. Negative 2 plus minus 2. So the one vertex is going to be as to negative 2 plus 2, 0, 1. The other vertex is going to be negative 4, 1. And let's graph this ellipse now. And it's going to be in a horizontal ellipse. So let me create my oval. Well, instead of the creating oval, I'm going to actually do that. That's our ellipse. I'm going to show you step by step how to do it rather than just showing you the oval or the ellipse. Let's see the center. First, I need to locate the center, -2 and 1. So let's say that's the center. Okay. And then from that, we're going to go to vertices. -2. A was 2. So we go to the right 2, left 2. So on the left, we land on -4. To the right, we go to 0. Okay. I'm just going off of here. Again, A is 2 and B is 1. Square root of 1. Square root of the denominator. So B is 1. B, the endpoint of covertices. So from the center, I'm going to go down 1 and up 1. You see how that works? And then I'm going to try to draw my ellipse this way. That's portion. And here's the other portion of it. You see how that works? And there, now I got all these key points. This point is V and then the other one V prime. Right, the V is -4, 1. This one is at 0, 4. And this is 4. Oh, I'm sorry, that's actually 1. 4 was the, or -4, 1 is this one. There you go. Okay, these points, these are collinear points. They have the same height of 1. That distance is 1. Okay, now where are the foci? Well, the foci are at -2, and then I go to the right, square root of 3, to the left, square root of 3. Square root of 3 is about 1.7. So -2 plus 1.7 puts me at near the vertex here. Puts me at negative point. So there you go. Here's 1 point. -2 plus √3 comma 1. That's one focal point. The other focal point is here, which is at -2 minus √3 comma 1. That's about -3.7-ish. And there we have the complete graph and all the key points that we wanted to label. All right. Now, again, let's finish this one with a word problem and application, if you will. So I'm going to go ahead and grab one of the applications from the book, copy it, and we'll discuss it. All right, here is the exercise we're going to look at. An example with whispering galleries. Jim, standing at one focus of a whispering gallery, is 6 feet from the nearest wall. His friend is standing at the other focus, 100 feet away. What is the length of this whispering gallery, and how high is its elliptical ceiling at the center? All right, so putting these numbers to work. Well, we were told that, let's see, focus 6 feet. So this is one focus. So the focus is going to be, we're going to make this focus somewhere here, let's say. And the other focus would be here. That's where his friend's at, right? His friend is got to be exactly located at the other focal point. Again, the reflexive property, by the way, the reflexive property of the ellipse is this. Any ray that comes from one focal point hits no matter where on the ellipse, it will reflect onto the other focal point. So there you go. That's why in whispering galleries, if a person's standing in one focal point and simply looks up to the ceiling, and remember, there is no floor, there's no elliptical portion, this is the floor, right? They're standing on the floor. This part doesn't really exist. All right. So anywhere they can talk to, like for example, they could be not facing each other and they'll be talking to that point, the ceiling, and that will reflect clearly to the other side. The person, his friend, can be talking to the ceiling in front of him, behind his friend, and that will reflect towards Jim. All right. Oops, I didn't want to do that. Sorry about that. Hold on. Okay, so we are back to what I had. All right, so it's because of that reflexive property again that they can communicate with one another. Now let's put the specifics to work here. Now we're told Jim is on the focus 6 feet from the nearest wall. Now it doesn't matter whether it's on the right or left focus. I'm just going to take it to be the right side for simplicity because things are positive on the right side. So this is where the wall is, right? We're told that he is 6 feet from the wall. That distance is 6 feet, and this is not going to be drawn to scale. His friend on the other focus is 100 feet away from him. So that means the distance from one focal point to the other focal point, this is 100 feet. Correct? So by symmetry, therefore, if that's the center, this is going to be 50. And remember, that's going to be our, C, isn't it? C is the distance from center to a focus or a focal point. That's going to be 50 feet away. So we got the C going on here. And then because we have C, and I can also use the information that's given to find the distance from center to a vertex. The wall would actually act as a vertex. The transverse axis is horizontal here, right? The longer of the two axes. So the major is horizontal, the transverse horizontal, the minor is vertical. And that's going to be how long? That's going to be 56 feet, correct? And therefore A is going to be 56 feet. The distance, A is distance from center to a vertex. And from this we can get actually B now, right? We can solve for B, and we have the equation C squared is A squared minus B squared, right? The longer of the two is horizontal, so A goes with X, and C here is 50 squared is equal to 56 squared minus B squared. And 50 squared, that's 2500. Subtract 56 squared. 56 squared is going to be 3136, and that's equal to negative B squared. So B squared is going to be 636 positive, therefore B is the square root of that, right? Which is going to be approximately about 25.2 feet. That's the distance, again, from the center to the end point of the minor axis, which happens to be the height of that elliptical ceiling at the center. This distance is 20, its coordinates are 0 and 25.2. That's what this is. Cool. So we answered actually the last question. So what about the first part of that question? What is the length of Whispering Gallery? Well, the length of it is going to be the distance from one vertex to the other vertex, right? The length is the length of the major axis. There you go. That's the length. Again, we just established that this distance is 56. By symmetry, the other side is also 56 feet. So the entire distance, the length of the Whispering Gallery is going to be the sum of those two, or 112 feet. That's how long the gallery is. and that's it. I guess that's all we wanted to do. Now, if you want the equation, by the way, we don't need to find the equation. As you can see, we answered the question, but the equation would be, because center is at 0, 0, is x squared over a squared plus y squared over b squared equal 1. And a is the greater of the two. 56 square that, so it's 3136, right? plus y squared over b squared, which is 636. That's even the equation of that ceiling, the elliptical ceiling. There you have it. The problem did not ask for that one, the equation of the elliptical ceiling. And that's it. So not too bad. Again, we are done with all we need to talk about ellipses for our work anyways. And as always, thank you for watching, and hope to have you in another lecture, in another video. Thank you, everyone. Cheers.